All right, so this is another set of trigonometry identities, and the main aim of most of these identities is to simplify the work of students. So instead of going on to trying to prove every single detail on that trigonometry, what you have is just some simplified set of rules that gives you a much better chance of getting your solutions. So for instance, wherever you see sine x, this x here actually signifies any angle. So when you have the sine of an angle, probably you are told to prove something on that trigonometry. What you want to do is to remember this set of rules that the sine of an angle can also be written as this. And most of these identities, you need to learn how to make use of them because it all depends on your destinations. If you are moving towards a particular answer, probably you're told to prove something is something, then you may decide to use sine x as this. So you need to be very versatile with every of these identities so that you will know exactly when and how to use them. So this is for cos x now. You see for cos x, we have three different formats. That means you could write cos x as this. You are okay with doing that. You could write it as this, and you could also write it as this third one. And for tan x, you can see how the identity of tan x is written. So these are, of course, I'm sure you remember that tan x also is also sine x over cos x. So it all depends on the type of question you are solving, and you would know exactly when you're supposed to use one or the other. Now, one of the things you can notice is this looks very closely like that of the sine 2x. If you remember, sine 2x was equals to 2 sine x cos x. But the difference between sine 2x and sine x is that we are having, instead of 2 sine x, we are having 2 sine 1 over 2x. So every other one here also looks like cos 2x, looks like tan 2x. The difference is that you are having 1 over 2, 1 over 2. So if you check the video on double angle, you will see that this set of identities are very identical with them. All right, let's see an application of this particular identity. So I advise you write this identity somewhere because we'll be making use of them in the next question we want to solve. So looking at this particular question, you can see we are having sine theta, we are having cos theta. We're told to prove that this left-hand side is equals to this right-hand side. So this is a very important application of the identity I just showed. One of the things you have to do quickly is to fix those identities into this particular left-hand side. And let's see how we go from there. So when we have this, we obviously know that our sine theta from that identity will be written as 2 sine, of course, theta over 2. That's based on the last identity I just wrote, theta over 2. And this will be minus cos theta. Obviously, cos theta was 1. In this case, we'll be using the third scenario. I'll be telling you why we'll be using the third scenario in a while. So we'll be using this particular format of cos theta, then plus 1. Of course, this is me fixing in our identities in. This is sine theta here. This is cos theta here. And this is plus 1. So we have the same thing happening beneath, just that the difference with the sign. So we have theta over 2 cos theta over 2 plus, in this case, the same cos theta. We'll be using this format also. And this one is minus 1. So if you go on to expand this, you will get 2 sine theta over 2 cos theta over 2. This will be minus 1, then plus 2 sine square theta over 2 plus 1. Everything over 2 sine theta over 2 cos theta over 2. In this case, this is plus 1 minus 2 sine square theta over 2 minus 1. So looking at what we have here, I'm sure you agree with me that this minus 1 here will cancel this 1 here, and this plus 1 here will cancel what we have here. So we are able to get a more simplified version of this function. So bringing out the resultant, we have 2 sine theta over 2 cos theta over 2 plus 2 sine square theta over 2, everything over 2 sine theta over 2 cos theta over 2. In this case, this is minus 2 sine square theta over 2. So earlier I told you I was going to explain to you why we decided to use the third version of cos theta. But you can see the reason why, because in this case now, you can see from here, I can factorize my sine square theta over 2 out, because I can see sine square theta over 2 is on this side and is on this side. So these two, the factors 2 sine theta over 2 is present in both of them. So I won't be wrong if I bring out 2 sine theta over 2, and then I'll be having a resultant of cos theta over 2, and in this case plus, we'll be left with just 1 here, because we'll be left with only sine theta over 2, because we have brought out 2 sine theta over 2. So we're left with sine theta over 2 here. Everything over, we have the same thing, we factorize 2 sine theta over 2, and then we'll be left with cos theta over 2 minus, we're left with just 1 sine theta over 2. So this is the reason why, of course, if you use the other version of cos, you would also be able to factorize cos out. But I decided to use that of the third version of cos theta, which makes it easy for me to factorize sine theta over 2. So from what we can see here, it's obvious that we can cut these two versions, the upper and the lower, because they are both the same thing. So what we're left with is cos theta over 2 plus sine theta over 2 over cos theta over 2 minus sine theta over 2. So we're going to do something very interesting now, because we want to try and modify this work. So this is what we're going to do. We're going to be multiplying by 1, but the one we're going to multiply by will be in this format. And I'll tell you why we're going to be doing that. We're going to multiply this particular function with cos theta over 2 minus sine theta over 2, and over, of course, the same thing. That was why I said we're multiplying by 1, because we are just writing the same thing. We just want to change the form. So essentially we are multiplying by 1, because this over this is 1, but we want to change this form. We want to use this to help us with this, our equation. We want to modify this equation, because if you can look at what we have here, this and this, if I meet this with this particular function here, if I meet it with this particular function here, I'll be getting something that will be much more easier to solve. So that's why I introduced this here, so that we'll be able to make a good solution out of this. So multiplying this with this, of course, if you remember your difference of two squares, you will know that when you have a plus b and a minus b, this will be giving you a square minus b square. This is what we call difference of two square. So, and you can see that this is more like, if this was a, if this was b, you can see it is something plus something, then the same thing here minus the same thing here. So this matches up. So I can write this numerator now as cos square theta over 2 minus, don't forget, difference of 2 square, sine square theta over 2. This is me just using my understanding of factorization. So I'm able to bring this down to this. Now, if you can see something going on here, and the reason why we needed to do this is that this particular thing I wrote here, this particular thing, this thing here, is the same thing as cos theta. based on our identity that I wrote earlier. So you can see the reason why we wanted to do something like that. Now, if we decide to multiply the denominator, this times this obviously will be cos squared theta over 2. This times this will give me minus sine theta over 2 cos theta over 2. This times this will also give me the same thing, minus sine theta over 2 cos theta over 2. And this times this will give me plus sine theta sine square. This times this now will give me plus sine square theta over 2. So if you look at this clearly, you will see that I can change my denominator because this and this. So I will just be solving for the denominator alone here. So my denominator will, I can make this, I can have this as cos square theta over 2 plus sine square theta over 2. Then this 2 will obviously be minus 2, because they are the same thing, minus 2 sine theta over 2 cos theta over 2. This is for the denominator alone. So this is me just trying to, this is for the denominator alone. So we can go on to bring them together and you will see how great this is. Now keep in mind that this is the numerator and this is our denominator, which I modified from here. Now, if you look at what we have here, if you look through on your identity, the one I just showed you some minutes ago, you would see that this thing we have here, this function here, is the same thing as cos theta. So I can write cos theta over, now this is our denominator. I'm sure you recollect the identity that told you that when you have cos square of an angle plus sine square of an angle, based on your basic identity, that's equals to 1. This is an identity. Cos square theta plus sine square theta is equals to 1. Now, I hope you don't get it confused that you are asking that, but you have theta over 2 here. The meaning of sine square, so the meaning of sine square theta plus cos square theta in your basic identity being equals to 1. This theta here doesn't necessarily mean it has to be theta, like theta. So this was a dummy for any angle. So that means the sine square, the sine square of an angle plus the cos square of an angle. So in this particular case, the angle here is actually theta over 2. So it also still applies. So don't get confused with theta over 2 being there. What that identity was actually saying was that the sine square of any angle plus the cos square of that same angle. So as long as it's the same angle in both cases, it's equals to 1. So that means I can essentially change this whole place, this whole cos square theta over 2 plus sine square theta over 2. I can change it to 1. And can you people, can you look through on this and tell me what particular, what identity this is? This was written some few minutes ago. Well, if you look properly well, you would see that this is actually the identity for sine theta. Of course, in the identity I wrote, I used x as the angle. But in this case, we are dealing with theta, so you should know how to always make the changes around that. So that means I can really write this as minus, this is sine x. So you see that this is sine x. So you can see that we have brought this whole voluminous complex function to just this, because we understand our identity and we know that this is cos theta, this is sine. I wrote x, I should have written theta. We're not dealing with x here. And this whole thing we have here is 1. So what's the next thing to do? So I want you to know that cos theta over 1 minus sine theta, I'm not wrong if I write this as 1 over, that means having the 1 minus sine theta over cos theta. This, what I wrote here, this particular value here, what is here, is the same thing as what is here. For those of you that you're probably having an issue in understanding what I just did, but you can go on to examine it. This is 1 divided by 1 minus sine theta over cos theta. Of course, if I'm changing this to times, I'm changing this to cos theta over 1 minus sine theta, which is still the same thing as this. So, but just for the sake of, I told you already that your direction determines how you go about things. So I can see that I'm moving towards 1 over sec theta minus tan theta. So obviously, I want to be seeing something that looks like this. So I brought up the idea of making this up. All right, so if you look through on this, you can see that the solution to what you're told to prove is very much feasible. So all you need to do now is to separate this fraction and you'll be seeing your answer. So if you go on to separate this fraction, you'll be having 1 over, this will be 1 over cos theta minus sin theta over cos theta. Obviously, this will be 1 over cos theta from our basic identity is given as sec theta, and sin theta over cos theta is given as tan theta. So you can see already that from this, we have been able to prove that the left-hand side is equals to the right-hand side. All right, guys, thank you for joining. I really hope you enjoyed the video. I hope to see you in the next video. Bye-bye.